This conference will now be recorded.
Hello everyone, the topics that we are going to discuss today, ionic versus covalent bond, because individually we have seen what is ionic bond, what is covalent bond. We will now compare them. Lattice energy, bond number cycle, variable electrovalency, variable covalency, coordinate bond and hydrogen bond. Here we have two pictorial representation. One is for ionic bond and another one is for covalent bond. So for ionic bond, that is the first one. Here we have a pattern, very simple picture. So in this pattern, this red electron that you are seeing, that is donated from this pattern towards the other molecule. So that is why I'm calling it cation, and the second one is anion. And this positive charge that you are seeing, that is actually the nucleus. Fine. So after donation of this electron, there is formation of positive ion or cation, and now both the electrons, because this is originally present in the right hand side atom, and now this new electron is also added to this, that is donated. So direction of donation from the left atom to the right atom, and after that there is formation of positive ion and there is formation of negative ion, because now you cannot call them atom. Initially you call them atom. This is one atom, this is another atom, but once electron donated from atom, left atom to right atom, now you have to call them positive ion or negative ion, because there is generation of positive charge. Don't be confused with the positive charge of nucleus, that is completely different. And this positive charge is because of loss of electron, and there is negative charge generation in the right hand side atom. So this interaction between these two positively charged species, one is positively charged, another one is negatively charged, an electrostatic interaction between these two oppositely charged species, that interaction is actually ionic bond. But when it is covalent bond, there is no question of donation. Now this electron, and there is another electron from the right hand side atom. This is atom, this is also atom. Okay, and these two electrons, after covalent bond formation, they are equally shared by both these atoms simultaneously. So that is why it is covalent bond. There is no formation of ion, positive ion or negative ion. Now if we compare them, ionic bond, covalent bond, ionic bonds mainly you will see between metal and non-metal. Okay, now metal, that is actually a different types of bond, which is metallic bond, that will be discussed not now, later. But mostly it is between non-metal and metal. So for example, suppose you have potassium and chlorine. Potassium has donated electron, now it is K plus. After donation it is K plus, and Cl accepting electron, it is now negative. So this is non-metal, chlorine, and metal is potassium. So interaction between non-metal metal, mostly we get ionic bond. And covalent bond is formed when there are two non-metal atoms. If you consider chlorine atom, basically chlorine diatomic molecule, that is Cl2 I am talking about. If you consider this molecule, here both these atoms, they are basically non-metal. Okay. Then the second point, total transfer of electron. But in this case, it is basically sharing of electrons. Then the next point, high melting and boiling point. So here we have electrostatic interaction between cation and anion, and this interaction is very strong. So that is why when we change the phase, that is from solid phase to liquid phase, that is actually the melting point, the temperature at which solid is converted to liquid, and that is melting point, and boiling point is the temperature at which liquid is converted to vapor. Okay, so both this temperature, melting point, boiling point, that is comparatively high when there is ionic bond present in any ionic compound, and in case of covalent is comparatively low melting, and boiling points, these are close to room temperature. Ionic compounds, they are mainly solids at room temperature, for example KCl, NaCl. But when we are talking about covalent molecule, they are liquids or gaseous at room temperature. Because see, you just don't have to remember this, there is a particular logic behind all these properties. Because solid means what? the interaction between the individual molecules, that is very strong. So that is why they are mostly solid at room temperature. But when it is covalent bond, compared to ionic bond, now the interaction is not so strong. So that is why the molecules are comparatively far from each other. So that is why they are liquid or gaseous, because that is the basic difference between solid, liquid and gaseous. That is what is the distance present between two atoms or two molecules. If it is very close, they will form solid phase, that is solid will be their physical state. If it is intermediate distance, it will be liquid, and if it is very high distance between two atoms or molecules, it will be gaseous at room temperature. Then ionic compounds, mostly inorganic compounds, they are hard and brittle nature, but here relatively soft nature, and you will mostly find covalent compounds in organic chemistry, not inorganic. Strong bond, weak bond, electrically reactive, doesn't normally conduct electricity because there is no charge present, no positive charge or negative charge. Soluble in water, insoluble in water. Now why it is soluble in water? Because if you consider water, it has some polar nature, and ionic bond there is also some polar nature, and polar likes polar species, so that is why it is soluble in water, unlike covalent molecules. Electron orbitals are separate, electron orbitals overlap, and it has to be because there is proper sharing of electrons. So if orbitals are not overlapping, how this sharing will take place? So overlap is obviously necessary, but if you consider ionic bonds, one is completely donating electron to the other species. So electron orbital, even if there is no overlap, it doesn't matter anything. Okay, so these are some points based on which you can compare ionic compounds and covalent compounds, or you can say ionic bond or covalent bond. Lattice energy. Now lattice energy, it is this term basically we are getting from electrovalent bond or ionic bond. So we have already seen what is ionic bond with the example K plus Cl minus, that is potassium chloride. With this example basically in last class we have seen what is ionic compound, what is ionic bond, and now once you know what is ionic bond and the compounds where this ionic bond is present, you can call them ionic compound. And for ionic compounds mainly this term, that is lattice energy term, is applicable. So as we know that ionic compounds, they form crystal, right? So lattice energy is the energy required to 1 mole of an ionic crystal, required to break 1 mole of an ionic crystal. Sorry, let me read it once more. Okay, it is the energy required which is given to this 1 mole of ionic crystal. And what is the purpose of providing this amount of energy? In order to separate it into gaseous ions in a vacuum via an endothermic process. So suppose you have already ionic crystal. Just take the example of potassium chloride. You have ionic compound potassium chloride. It has formed a crystal. Now what you are trying to do, individual K plus ion and Cl minus ion, they are obviously in ionic crystal, they are close to each other. That is, there is a particular pattern. Okay, picture also I have already shown in the last class. But now what you are trying to do, you are trying to separate all the K plus ion, Cl minus ion into individual gaseous ion in a vacuum. So you are basically destroying all this electrostatic interaction between cation and anion, and you are making all these ions far from each other. So now they are individual free gaseous ions in vacuum. So when you are trying to do this process, obviously you have to apply energy. So this is an energy which is required. Okay, or you can say it is the energy supplied to 1 mole of an ionic crystal for the purpose of separation of all these cations and anions in free condition in a vacuum. And this process, as you are supplying energy, so it will be endothermic process. Similarly, you can also consider the reverse process. Suppose there is already several K plus ions or several Cl minus ions are present in free condition far from each other in vacuum, and now you are bringing close to each other and you are forming ionic crystal. In that case, that process will be exothermic because energy will be released. From unstable condition, you are going to stable condition because you are making the lattice starting from free ions. So that is, you are making something more stable. So in that case, energy will be released. But when it is the other way around, that is when you are breaking the crystal, obviously you now have to apply energy because it is energy requiring process. So that is, it is endothermic. So you can give the definition of lattice energy in both ways. So this statement is actually considered. So whether it is endothermic or exothermic, if you consider the other energy, that is when you are bringing all the free ions and you are making the crystal, in that case energy will be released. So both these processes basically will involve the same value, same numerical value of energy. Only difference is in this case you have to supply energy, but when you are bringing all the ions together, you are making the crystal, in that case energy will be released. Otherwise numerical value of energy is same. Only when you are breaking it, it will be you have to supply energy which is positive, that is endothermic, and when you are doing the reverse process, in that case energy is released, or you can say it is exothermic process. So lattice energy is basically a measure of strength of ionic bonds in an ionic compound, because when you are supplying lattice energy, you are basically breaking all the ionic interaction, all the electrostatic interaction between the cation and anion. Okay, so if lattice energy is very high, you have to provide very high energy. That means the ionic bonds are very strong. So maybe you are having two different compounds, both are ionic, but in one case you are supplying more energy, in the other case you are supplying less energy. That means the first system is having stronger ionic bond compared to the second case. So that is why it is mentioned here. It is a measure of strength of ionic bond. So if lattice energy high, strength of ionic bond is also high. It provides insight into several properties of ionic solid, including volatility, solubility, and hardness. Okay, so if you have if you know the value of lattice energy, you can also get some insight related to all these properties: volatility, solubility, hardness. Okay, then lattice energy of an ionic solid, it cannot be measured directly, and for its measurement, basically we take the help of Born-Haber cycle. Though Born-Haber cycle is also present in another unit of thermodynamics, but here also we will have preliminary idea about Born-Haber cycle, so that you can understand that how lattice energy is actually calculated, because directly we cannot measure it. Okay. Now sometimes a confusion may arise, because in some books you may find that it is mentioned lattice energy, in some books it is mentioned lattice enthalpy. So what is the difference between? Basically enthalpy and energy both are having same unit, which is the energy unit, joule. Okay, in short, J. So in both cases we can use this energy term, but there is a subtle difference between these two. When it is a lattice energy, it is denoted by this U sign, del lat U. Now this is equal to del lat H, which is basically enthalpy. So this equation basically we are getting U equal to H minus PV. So this type of equation is very common in thermodynamics, though thermodynamics we have not yet discussed. But remember, U here, this lattice energy is equal to H, that is enthalpy sign, minus pressure and volume. Now pressure is fixed and there is a change in the value, so that is why del sign is used. And del lat U, this is molar lattice energy. That means it is a lattice energy for a particular amount, and that particular amount is 1 mole. So that is why molar lattice energy. Similarly, this is molar lattice enthalpy, and del BM molar volume change, and P is pressure. Okay, now left hand side already joule unit that you can understand. Now this is also joule, but if you are thinking what is the unit of this, it will be, so in SI method, if you consider pressure unit Pascal and volume is meter cube, so Pascal into meter cube, that is also joule. So ultimately this will also be joule. Left hand side is joule, right hand side is also joule. Okay, so these two terms you can use for the same purpose, because when lattice enthalpy is high, basically lattice energy is also high, and vice versa. But there is a, this is the quantity by which there will be some difference. Otherwise these two you can use for the same purpose. Fine. So here you can see a representation of Bond-Haber cycle. So in this case, we have taken the example of potassium chloride crystal. Okay, here we have KCl in bracket. What is mentioned? It is solid. So it is KCl solid. Now, when you are having this KCl solid, you can make it in different way. So if you consider this potassium in solid state and chlorine in gaseous state, in bracket it is mentioned G, but we do not need 2 chlorine atom, we just need 1 chlorine, so that is why half chlorine. Here we have a term del HF naught. Now this is the it means it is enthalpy of formation. F is F for formation. So when you are making 1 mole of KCl solid, starting from its constituent elements means potassium is one element, chlorine is another element. From its constituent elements under normal condition. Now under normal condition, what is the physical state of potassium? It is solid. Under normal condition, chlorine remains in gaseous state. That means it will be gaseous. So that is why these two physical state must be S and G. You cannot take gaseous potassium, or you cannot take liquid chlorine or solid chlorine. Okay, the physical state, when you are defining enthalpy of formation, the physical state of the constituent must be the normal physical state under normal condition. So now you are getting, when you are having this del H F naught, this enthalpy, you are having KCl solid. But you can also make KCl solid via some other path. So what are those paths? See what we have done here. Potassium solid, first you can convert to gaseous potassium, and for that you have to provide some energy, which is enthalpy of sublimation. See what is mentioned, del H sub. Then this gaseous potassium, next what you have to do, you have to remove 1 electron so that you can get the corresponding cation. For that you have to provide ionization energy. So this is actually ionization enthalpy. Okay, so this is one side for potassium. What about chlorine? Chlorine, first you are dissociating. That means chlorine is diatomic. If you break the bond between two Cl, you can get chlorine gaseous. So del H dissociation energy we are providing. Then chlorine gaseous, we are converting it to the corresponding anode. And for that what you will do? You will add 1 electron, which means electron gain enthalpy or electron affinity. That energy will be involved here. Once you have obtained K plus and Cl minus, because these two are also now in gaseous state, though that is not mentioned here, but it is still in gaseous state. Now these two together you have taken and you are getting KCl solid. In this case, the amount of energy that will be involved is lattice energy. So when you are moving from this individual K plus and Cl minus towards KCl, basically energy will be released. But if you are moving in the opposite direction, that is you are breaking KCl solid and you are getting K plus gaseous, Cl minus gaseous, in that case you have to provide the same amount of energy. But now you have to supply. In the previous case it is released energy, in this case now you have to supply. That is the difference. Okay, now you can take any of this path. Now, here some thermodynamics idea is required. Basically, this Born-Haber cycle is under thermodynamics, but still we are discussing it here so that you can get some idea about ionic crystal and how to calculate lattice energy. So in this case, if you simply focus on this path, that is one path, or you can go via this path. Okay, so these two together. Now, as enthalpy is state function in thermodynamics, there are two types of function: path function and state function. So for state function, the definition is these functions. In this case, it is basically I'm talking about enthalpy because all these signs are you see del H. So enthalpy is state function. It doesn't depend on which path you have taken. You are trying to make KCL solid. So whether you move to this direction or through this direction, that is not important. So that is the reason the summation of all these individual terms, if you consider, and then this lattice energy, all these 5 terms, del H sub, del H I, del H EA, del H dissociation and U, all these together will be equal to del H F naught, because you are, that is the direct path. If you directly move from, if you directly focus on this path, it is direct path, but you can also move through via other path. So this via path, paths basically plural, that will be equal to this single del H F naught, because I can also give you a simple representation. Suppose you are moving from the point A to B. So here energy enthalpy is involved del H. Okay. Or suppose you are moving first A to C and then you are going to B. That means now you are not moving from A to B directly. You are going first to C, then you are moving from C to B. And in this case, it is del H 1 and this is del H2. So as it is state function, you can say that del H is equal to del H1 plus del H2. So same thing I am also applying here. And that is possible only for state function, not for any path function. So here all the terms that are involved, what those terms actually mean, that is mentioned clearly. Del H sub sublimation energy, which means you are converting solid to gaseous. Del H dissociation, the energy required for bond breaking. Then ionization energy or enthalpy, electron affinity, enthalpy of formation, and lattice energy. Now this del H F naught that is related to other terms, and how that you will see. So Born-Haber cycle enables us to understand the overall reaction process through a series of steps. It involves several steps such as affinity, ionization energy, sublimation energy, etc., etc. You have already seen all these terms. And this Born-Haber cycle is based on Hess's law. Now, what if this law states? This law states that the overall change in energy of a process can be determined by breaking the process down into some steps. Then you can add all the changes in energy of each step. So that we have done here. And see here, del H F naught. That means this enthalpy of formation, that is actually equal to all these 5 terms. Okay, so this is the direct path. When you are moving from, you are just involving this equation. But there are some via paths. If you consider all of this, then you have to add all these individual terms, which is equal to this one. Now here, if suppose you want to calculate U, which is basically lattice energy. So obviously the other terms, all those values should be known. Then only you can calculate U. Okay, or maybe that U is known and some other terms are also known. You have to find del H sub, or all the terms in the right hand side of the equations are known. You have to find del H F naught. So any that is one of the variable may be unknown and rest of the variables known. Only then you can calculate it. Now we will solve one problem. So same equation again is written, And see, now U is taken in the, that is in the, it is present, that is, it is only U is present in the left hand side. That means now del H sub it will be negative, this will be negative, everything will be negative, right? All these four terms you have taken the towards the side of del H F naught. So this is positive, rest of the parts are negative. There is a negative sign because you have changed the side of the equation. Now del H sub, the value is 89. Then del H IE, the value is 418.8 joule. All these are basically not joule, kilojoule. Then dissociation, basically you have to take half of del H dissociation. You are taking only one Cl. So when you are breaking chlorine, basically you are getting 2 chlorine atoms, but you just need one. So that is why whatever is the del H dissociation value, you have to divide it by 2. And del H EA, you know, electron affinity is already negative. So that is why within bracket there is a negative sign, negative will be cancelled. And del H F naught, remember enthalpy of formation is mostly negative. So if you add all this, you can get the value of U for potassium chloride, which is minus 716.8 kilojoule per mole. Another example of ionic compound here we have taken, which is MgF2, magnesium fluoride. Now compared to the previous process, it is to some extent different. What is the difference? Here in the previous case, there is only one cation, only one anion. Simple K plus Cl minus. But now you have Mg2 plus and 2 fluoride ion. That is the only difference. Now anion increased. One anion is increased. If you directly making MgF2 starting from its constituent elements, solid magnesium and gaseous fluorine, that is their natural physical state. Okay, and that is the metal is solid, the non-metal is gaseous. So this is the direct path, and the enthalpy involved, enthalpy of formation del H F naught. Now if you are first using this del H sublimation, Mg will be converted to gaseous state starting from solid to gaseous. That is actually sublimation process, and the corresponding energy del H sub. Then you have to remove 2 electrons. So now only one ionization energy is not enough. Ionization energy del H IE 1, then you are getting Mg plus, then another electron you have to remove. Now del H IE2 and Mg2 plus is already formed. Come to the non-metal now. Dissociation energy, and here we will not take half dissociation because both the fluorine is liquid. And del H electron affinity. So you are feeding 2 electron and you are getting 2F minus. Now once you have obtained 2F minus in gaseous state and Mg2 plus in gaseous state, these two will combine, and now the energy involved is lattice energy. Okay, so this will give you MgF2. Now all the values for these terms, del H sub, which is most always positive, del H dissociation always positive, ionization energy first. See, the second one is always high, that we know already, and ionization energy always positive. Electron affinity negative, and del H F naught, which is always negative, minus 1124. Now if we use this equation, this type of equation, so we have, as we are calculating lattice energy, so U is on one side and all the other terms on the other side. So we have this 146.4, which is for del H sublimation, first ionization energy, second ionization energy, del H dissociation energy, then 2 into electron affinity because you are feeding 2 electron, F minus 2 times. Starting from F to F minus, we were doing it 2 times. That is a 2 into electron affinity. And as usual, del H F naught. So this is the lattice energy. Now this lattice energy you will always get in negative form. Why? Because in this bond Haber cycle, if you look at the bond reverse cycle carefully, the energy, lattice energy that is involved, it is for the process where free anion cation you are bringing together, you are making the solid. That means from unstable to stable you are moving. So energy will be released. But if you are breaking MgF2 and then you are getting individual F minus Mg2 plus, obviously, then the same amount of energy you have to now provide. In that case, it is endothermic, plus 2957.8. But in this case, we are getting this calculation. From this calculation, the lattice energy that you are getting, obviously, it will be negative. Because in that way, this bond reverse cycle is designed. Fine. Next is variable electrovalency. So electrovalency, that term is basically coming from ionic bond. So when you are, you have already seen several examples of ionic compounds. Just take the example of MgF2, the last that we have discussed. So in this case, the oxidation state of Mg is 2+. So here I can say that electrovalency is 2+. Similarly for F, it is -1. Or simply you can use the numerical value. For Mg it is 2, for F it is 1. But so for magnesium it is always 2. You will never see magnesium plus ion or magnesium 3+, because that is not possible. If you write the electronic configuration, you will see when it has lost 2 electron, it will reach noble gas configuration. So that is why Mg2+ is the only electrovalency possible for Mg. But there are some cases where for the same element you can get more than one electrovalency. So that is why it is variable electrovalency. The electrovalency of an element is equal to the number of electrons lost or gained by its atom during formation of ionic bond. Now, S block elements, as I have said, Mg is basically S block, group number 2 alkaline earth metal. You will see S block elements. S block element means basically group 1 alkali metal, group 2 alkaline earth metal. So for group 1 and group 2, that is S block, you will not find any variable valence. It is always fixed. The oxidation state for group 1 is +1 always. For group 2, it is always +2. It is never variable. But in p block elements, especially with higher atomic numbers, okay, so higher atomic numbers, mainly if you consider the lower part of p block, that is as you move down the group, the lower part, all the metals are present, tin, lead, all these metals are present there, right? So here I am mainly talking about all those metals. So they show variable valence, because if you consider non-metals of the p block, they mainly form covalent bonds. So you cannot use the term electrovalency. So I am basically focusing on the metals in the p block. So they show variable valence. And also F block and D block, that means transition elements, which is for D block, inner transition elements, that is for A block. They are also variable valency observed. Now for F block, there is separate unit for that, why they show variable valency. Details will be discussed in that particular unit, but we can get a slight idea that why they show variable valence. Now here we have two examples. One is copper oxide. Basically both these are copper oxide, but two different types of copper oxide. The first one, it is cuprous oxide. Basically it is not cuprous, it is cuprous oxide. Now in this case, the oxidation state of copper is +1. In the second case, it is +2. So that is why the formula is also different. Oxygen, its valency is -2. To balance -2, only one copper 2 plus enough. So that is why the formula CuO. This is the oxidation state. So two different oxidation state possible for copper. That means it is showing variable electrovalency. Similarly for iron also, 2 plus 3 plus, both these states are possible, and depending on that, the formula of these two different iron oxide formula is also different. Okay, so these two are the example and both are from D block. Now the reasons for showing variable electrovalency, the reasons are mentioned in this box. When you consider p block elements, mainly inert pair effect is the reason. And what is inert pair effect we will discuss in the next slide. And what about transition elements or D block elements? Now in D block elements, what happens? You will see the electronic configuration of transition elements. It mostly involves ns and n-1d. Just take the first transition series. Ns is in this case 4s. So n-1 is 3d. So 3d, 4s, these are involved. If you consider the next series, it will be 5s, 4d. If you consider the next series, it will be 6s, 5d, because principal quantum number is 1 less. Now the energy difference between these 3d and 4s, because in D block elements, both 3d 4s or 4d 5s or 5d 6s, both are containing valence electrons. They take part in bonding. So that is why I am calling valence electrons. Now the energy difference between these 3d and 4s, 4d or 5s, 5d or 6s, in general you can say ns and n-1d. The energy difference is very, very small. Okay. So as a result, what happens? Sometimes it may happen that the electrons that are present in 4s, suppose 4s2 is the electronic configuration. Okay. And here we have some more electrons. Suppose I'm writing 3d5. So when 2 electrons from 4s involved, it will show +2 oxidation state. Suppose another electron from 3d is used up, so it will be now having oxidation state +3. So see, because of the small energy difference, electron can be removed from 4s, and 3d is not very different energy from 4s, so electron can also be removed from 3d. So this is the reason they are showing variable values. And when it is inner transition, that is A block, the third statement, now small energy difference between ns and n-2f. Remember, there are basically two series, 4f block, 5f block, or you can say lanthanides and actinides. So when it is 4f, basically n will be then 6. That means n is 6. So n-2, that will be 4. That means n-2f is 4f. Now the energy difference between 6s and 4f is very less. So electrons that are present in 4f, that can be used. Electrons that are present in 6s, that can also be used. So that is the reason. That is same type of explanation that we have already seen for D block element. Same type of explanation. Okay. But this much we will discuss for D block and A block. We will not go into further details. But what is inert pair effect and how it is, why it is responsible for showing variable electrovalency for P block, that we will see now. So here we have only P block in the right hand side picture. Let me write the groups, which is group 13, 14, 15, 16, 17, 18. This is second period. This is third, fourth, fifth, sixth. This is seventh. Okay. Now mainly this type of inert pair effect we consider for 13, 14, 15. These elements, mainly these elements. Okay. So as I have said, in the lower part of P block, because if you go to upper part, they are not metals. They are non-metals. They mostly form covalent bond. So the variable electrovalency, this term doesn't, it is not applicable for them, because electrovalency is all about ionic bond. Okay. Now why these elements that I have just marked, indium, tin, antimony, bismuth, helium, then PV, lead. Okay. So what happens here? So inert pair effect is the reluctance of ns2 electron to take part in bonding. Now ns2, it is mainly observed in 5th and 6th period. So ns will be 5s or 6s. Okay. To take part in bonding due to poor shielding effect of intervening d and f orbitals in post-transition elements. Now, if you observe these two row carefully, just before IN or just before TL, 49, 89, in this part, basically D block elements are present, right? Now here D block, it starts, this is the first series in the fourth period, this is the second series, this is the third series. That means these elements which we have just marked, these elements are basically post-transition elements. Post-transition elements means the elements that are coming after transition elements. Now, why we are giving so significance to this after transition elements? Because in transition elements there is D, and also A block is also filled, because A block is somewhere starting somewhere here. Okay, remember in group 3, after group 3 it starts. So that means before you have reached these elements, tin, antimony, lead, bismuth, you have already crossed the transition element. So that is why they are post transition. That means in their electronic configuration, F block electrons, inner F block, inner D block electrons are involved. Okay, now look at this picture. So just take the 6th period, that means 6s electrons are involved. Okay, now 6s, what do we know? The common electronic configuration, if we consider for P block, it is NS2 NP 1 to 6. That means this NS2 part is fixed, it will always be present. That is, in NS there will always be 2 electrons, whether it is 6s, 7s, whatever. So 6s, these two are the electrons that are present in 6s. You can take any example. Suppose I have chosen here PB. So PB is 6th period. That means, and it is from group 14. So its electronic configuration should be 6s to 6p2. That means in 6s 2 electrons are present. But remember, if you consider the inner electrons, 5d is already there. That is field 5d, field 4f, they are already present. So suppose this is field 4f and this is field 5d. But as we know, their screening property is very poor. As a result, this nucleus, it will direct have attraction for this 6s paired electron. And as a result, you cannot break this pair very easily. And when I'm saying you cannot break this pair very easily, what I'm trying to say, that individual to unpaired electron like this, you cannot get easily. So it will remain in paired condition. And the reason is poor screening of the intervening 5d and 4f electrons. Now, if you consider PB, as it is from group 14 with configuration, I'm writing it for just PB only, 6s to 6p2. Now, when it is using 2p or electrons, it will show oxidation state 2+. When it is also using these 2 electrons in 6s, it will show 4+. Okay, but which one will be more stable? Obviously 2+. The lesser one will be more stable, because if you want to get PB4+, you have to break this pair that is present in 6s, but this pair is inert pair. Why we are calling it inert pair? Because they do not take part in reaction. So that is the reason PB2+ will be more common than 4+, though 4+ is also there. And this is the reason why they are showing 2 different types of electrovalency. Similarly, you can take the previous element of PB, which is tin. Here it will be 5s2 5p2, but 2 different oxidation state, 2+, 4+. If you take the next period next group element, I mean group 15, antimony or bismuth. Now antimony and bismuth common configuration is NS2 NP3. So when they are using only 3p electron, they will show Sb3+, bismuth 3+. But if they want to show Sb5+ or Bi5+, then they also have to use these 2 electrons. That means this pair must be broken, but that is not so easy. And if you consider group 13, which is a common configuration is NH2 NP1. So when they are using only NP single electron, they will show this type of single oxidation state, and if they are also using the 2 electrons in NS, it will show 3 plus oxidation state. Fine. So what happens? There is increasing stability in the oxidation state, that is 2 less. That means 2 less means this 2 plus or this plus, that is the first one I am considering. This oxidation state will be more stable. So there is increasing stability in the oxidation state. Which one oxidation state? That is 2 less than the group valency. So what is group valency? Group valency is basically this higher oxidation state, 3 plus, 4 plus, 5 plus. Why I am saying group valency? Because if you focus on the groups, that is group 13 or 14, and how to understand valency, just consider this digit. So if you consider 3, 4, 5, that is actually the group valency. 3, 4, 5 group valency, that is present in the second row, 3 plus, 4 plus, 5 plus. But the oxidation state which is more stable, that is 2 less than the group valency. Okay, and that is only for 6s and that is 7th period. That is, it is mainly observed for 6th and 7th, because as you move down, this type of improper screening, inert pair defect, it will be more and more. So if I can ask you that among SN and PB, in which case inert pair defect will be more, it will be PB, because that is below SN. So as you move down, it will be more and more. Okay, and especially observe for groups 13, 14, 15 and 16. Here we have taken one PB compound, basically lead. This is also lead chloride, this is also lead chloride. Difference is here oxidation state of PB plus 4, here oxidation state of PB is plus 2. So plus 4 is less stable. So that is the reason PbCl4, even if it is formed, it will always be converted to PbCl2 and Cl2. That means 2 chlorine atoms removed in the form of diatomic chlorine molecule, and PbCl2 is formed, which is more stable because of its oxidation state 2 plus. Here you are seeing the electronic configuration of Pb. This is the Pb. See, outermost electronic configuration, it is from group 14. So total number of valence electron 4, but only these 2 electrons used for these 2 plus. But when both the electrons used, you will get 4 plus, but that is less stable. Fine. So if you look at this energy profile diagram, in this axis, as you move up, high energy, and this is basically the ground state. So before any excitation, this is 6s2, 6p2, that is the configuration. Now when it is you are supplying energy, this electron, now it will be shifted to here. So that is, it is in different color. Now you can see 4 separate unpaired electrons. So it will show plus 4 oxidation state. But this is imaginary. This is not happening very easily. What happens actually, reluctant 6s electron. So this type of depairing, that is breaking the pair and shifting the electron to 6p like this, that is not happening here. So that is why even if you are supplying energy, then you can see there is no change in the electronic configuration. Here also 2 unpaired electron, here also 2 unpaired electron. So it will show plus 2. If this type of expected excited state, if you consider, you can have plus 4, but that is expected, that is not actually happening. Okay. So after finishing variable electrovalency, variable covalency. So variable covalency refers to the tendency of certain atoms to show different covalencies. It is just like electrovalency, but now we are using the different term covalency or covalencies, because now we will talk about only covalent bond. So the valency that you observe in covalent bond, that you can call covalency. And the valency in electrovalent bond, electrovalence. That is the difference. Now mainly these atoms, I mean these elements, which elements? Halogens other than fluorine, that is except fluorine, then sulfur, phosphorus. So for these elements mainly variable covalency observed. Here we have taken iodine, and you can see for different compounds of iodine, all the compounds are compound between iodine and chlorine. So iodine is here the central atom, chlorine is not central atom. And in the first case only one chlorine, that means oxidation state of iodine is here +1. And why I am saying +1, because iodine and chlorine, if you individually consider, though both of them are non-metal, that is true, and there is covalent bond, but still if you consider which one there will be more positive charge, it is obviously iodine, because chlorine is more electronegative compared to iodine. So if you consider any polarity, obviously positive will be on iodine. It is more electropositive. So 1357, which is very clear from the formula. Similarly, when it is sulfur, if you consider simply group 16, then 6 should be the covalency, but it can also show 2 and 4. Okay. Similarly, if you consider halogen group 17, then the last digit 7 should be the covalency. 7 is present, but some other values are also present. So for sulfur also, except 6, which is the group covalency, other valency also we are seeing here. Similarly, phosphorus, which is group 15, so except this group covalency, you can also see 3. And accordingly, the formulas are changing. Though here phosphorus is forming compound, both are chlorine in both cases, but formula is different. Phosphorus trichloride, phosphorus pentachloride. So how it is happening? Here we have taken sulfur. So for sulfur, which is from group 16 and group 16, and period is 3rd. So its electronic outer usual configuration is 3s2 3p4. So that you can see here, 3s2 3p4. Now how many unpaired electrons are present? Suppose this is number 1. In number 1 picture, how many unpaired electrons present? Only 2. So when these 2 electrons are involved, it will form compound like SCl2. Come to the second one. Now one pair if you break, and if you shift the electron to 3D, in the second picture, how many unpaired electrons are there? 4 unpaired electrons. So now it will form compound like SF4. Now the remaining pair also, if you break, one more electron here. Now how many unpaired electrons? Total 6. Now it will form compound like SF6. Okay. So in this way, because of transfer of electron after applying energy, a number of unpaired electrons are increasing, and we are getting different covalence. So in the atoms exhibiting variable covalency, the number of unpaired electron increases as a result of excitation of the atom, and as a result you are getting different number of unpaired electron, and which leads to variable covalency. Here we have taken sulfur. You can also take iodine or phosphorus just for practice, and write the electronic configuration, then break the pairs and increase the number of unpaired electrons, and then you will be able to understand how variable covalency is possible for phosphorus or iodine. Fine, you can do it yourself. Here we have this problem. Variable covalency is exhibited by PS, NO, NP, and FCl. 4 examples are there. So see, it is mainly observed for which elements? What is mentioned here? Halogens, sulfur, and phosphorus. So there is no element that is present from second period, right? But if you look at the question, there is in some options there is in elements from second period, but that cannot be they cannot show any variable covalence. So that will not be correct. But we are lacking in time. We will finish the problem in the next class. Okay, we are almost at the end of the session. Thank you for listening.